Hi everyone, in this video I'm going to discuss the least squares formulation of Tikhonov regularization as well as its convergence in the small noise limit. So just recall that we're inverting for this initial condition M, and we're observing at a final time t the whole field U, and then finally we will find M such that f of M approximately equals D up to the noise. And then our regularized solution is given as follows. So the exact solution is this expression where we don't have the filter. We invert each eigenvalue, and then we essentially come up with its eigenbasis representation of the inverse. But because these alpha n's decay exponentially, 1 over the alpha n's increases exponentially, which leads to instability. And so we have some filter function to help mitigate this issue. So one way is to strictly truncate. Above some threshold beta, we allow the eigenvalue in. If the eigenvalue is too small, we just cut it off. And then a smooth version of that we call Tikhonov regularization. Now, in this video, we'll show a least squares formulation of Tikhonov. So I'm going to go right to the discrete case. We'll eventually come back to the continuous case of this problem. But we need to build some machinery before we get there, so I'm just going to go ahead and do this in discrete. So now we're talking about a vector in Rn. So this subscript tilde is just to tell you, hey, look, we're in the discrete case now. So we're going to actually discretize these operators through finite differences or however we want. And I might drop that tilde from time to time because we'll be working. Eventually it'll be clear that we're in the discrete case, and so sort of drop it. You might do it yourself as well. So the idea here, this is our formulation. And the idea here is that this is our data misfit, and let's choose purple. And this is a penalty term that penalizes large norm M. And the reason for this is that we want to fit the noise, or fit the data up to the level of noise and no further. So the idea is that, yeah, you might get, if you allow the norm to go very, very large, you might get, slightly smaller misfit, but that's probably because you're fitting noise, not because you're fitting data. It is basically the heuristic here. And so I'm going to go ahead and show you. The main goal here is to show that we actually get an expression similar to this one for the discrete case. So just for clarification here, M, this vector now, is just a vector that represents our actual N over L is, xn, so M is in Rn, d of y1 to d of ym, so this is in Rm with ym is M over L. In general, M and N are different, and generally M is much less than N. You have sparse observations to infer the field, and F then must be in m by n, right? Takes in, yes, m by n. So for this, I'll just present this with m equals n. Plus beta. And I'm going to call m beta to be the argmin over Rm in Rn of this problem, because we could choose tons of different beta. And so from here, if we take partial mi of that expression and set it to 0, that gives us the normal equations. And that is f star f plus beta I, m beta equals f star d. If you haven't seen that derivation before, this right here is basically the process. Not super terrible, and these are often referred to as the normal equations. That's what you get, and then it turns out that that's an invertible matrix, and then m beta is f star f plus beta I inverse f star d. So not too much to it. Similar to before, but we have slightly different operators. And so if I take f, let's see what this looks like in the eigenbasis. So if I take f as u, gamma, or not gamma, lambda, u star is u inverse, and lambda diagonal. So these are the eigenvalues. So it's unitarily diagonalizable. Why? Because these VNs form an orthonormal basis. In general, you always have an SVD, but so the logic of that will work the same. This will be slightly simpler as far as this problem, but in general, use an SVD. It'll work pretty much the same way. So let's look at f star. F, which is f squared, because if you just take the adjoint of that, you'll see that it's f squared. And so this is u lambda u star, oh no, u star u, sorry. U star u lambda u star, which is u lambda squared u star. And so this right here is the main property. U star u is the identity. And then you can go through and do all this, and basically it works out just like multiplying diagonal matrices. So you'll end up with u times lambda squared plus beta I inverse times lambda u star d is m beta, okay? And then this is still diagonal, right? You multiply diagonal matrices, it's just the product of their diagonals. And then if you invert them, it's just the reciprocal of their entries. And so this is diagonal with entries lambda n over lambda n squared plus beta. So that should look familiar. This is this sum. It is d dotted with un omega beta of lambda n squared times 1 over lambda n un, which looks exactly like this expression here, just with slightly different eigenvalues and eigenbases. And just note that, right, these lambda n's are not the alpha n of t's necessarily, because we've discretized the system. But they should approximate them as we refine the mesh, but also the lambda n in general should decay rapidly with n, which is the key point here. So you know, if we're not too close, we're generally going to capture the rapid decay. So the same instabilities are going to cause us issues. So that's to motivate that this formulation, this least squares formulation, works the same way. And if I do it continuous, and if this bothers you, this level of approximation, then if we do it in the continuous case, it'll come out to exactly be the same. So, but again, we have to build some more machinery for that. So just some comments. So over here, we have a nice Fourier representation in the continuous case, yada, yada, yada. But of course, we have to discretize at some level. The point is, if we use this least squares formulation, the main catch is we can solve this optimization problem without actually computing the eigenvalue decomposition and applying this filter on each level, whereas we kind of have to with truncated EVD or truncated SVD, because it doesn't have a nice formulation. There's theory built for least squares formulations to solve these things, solve that minimization problem fast, and things like that. There's packages available as well, so that you don't have to do that work. Now, notice also that this map, f of m, is actually linear in M, because it's just taking a Fourier series at the end of the day. So that's a linear map. If f of m is nonlinear, the least squares formulation still makes sense and can be solved, right? There's tons of packages out there for optimization, so it can still be solved. And yes, like I said, there's software available to do those types of things. Whereas you'd have to come up with a whole other formulation for nonlinearity to figure out a way to do something like this. And then finally, we can change norms to add info. I forgot to erase this section. Okay, we'll go over here. So what I mean by that is, I can take instead this problem. Min over m and Rn plus beta m r squared, where C and R are matrices and the C norm is C times X, 2 norm, and the R norm is Rx times this. So in our case, we had C equals the identity equals R. But this can be more general. So for example, if I take C equals 1, 0, 0, and so on, then that tells me that the first only the first component of the data matters. And the reason for that might be that, in your experiment, certain parts of the domain you're less confident in, so you weigh them differently. Now, of course, that's obviously an extreme example, but let's say, I have less and less confidence over the domain, and so I weigh, matching the data on one level. I care a lot more about it than other levels, and similarly, with R, you might have other reasons to weigh certain components differently. So that's the main attraction, I think, of this least squares formulation. And then the next video, I've went a little bit long here, so I'll do these. So in the next video, we'll do the convergence to show that m beta minus m true goes to 0 as beta and the noise level go to 0. And they have to go to 0 together in a certain way, basically. Because as the noise goes to 0, we want to decrease our regularization more and more to get closer and closer to the original problem. So they have to go to 0 together, and that's what we'll show in the next video. Thank you guys for watching.